Hello everybody, good evening and welcome to the Institution of Structural Engineers and welcome to this lecture on the investigation of the collapse of Champlain Towers South in Surfside, Florida. So before we start, I just have a little bit of housekeeping to run through. Fire exits are located at the front and the rear of the lecture theatre. We're not expecting any fire alarm tests this evening, so if the alarm does ring, we will need to evacuate the building. At the end of the presentation, we will have a question and answer session, and that will include an online audience. And please may I ask you to ensure that your mobile phones are switched to silent. So I need to read out this copyright notice. To the institution's best knowledge, copyright permission has been provided for all materials shown, and this broadcast is therefore presented in all good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed, or by agreement, an appropriate acknowledgement provided to accompany the e-conference. So before we move on to the main event, I'll introduce myself. My name is Paul Livesey. I'm a Chartered Structural Engineer, and I'm the Manager of Collaborative Reporting for Safer Structures. I'm very pleased to be the chair this evening, and I'd like to steal a couple of minutes of your time to briefly introduce CROSS and the work that we do. So CROSS is a confidential and secure reporting system that provides a route for professionals working with buildings and other structures to report the issues that they experience to enable lessons learned to be shared across the industry. At the heart of CROSS lies a strict no-blame culture, and we welcome reports about fire safety and structural safety issues, and these typically relate to concerns, near misses, and other incidents. So our roots date back to 1976, and we were first established to identify in advance trends and developments which might contribute to an increased risk to structural safety. The CROSS scheme itself was first launched in 2005, and it's based upon the success of confidential reporting in the aviation sector. In response to the Grenfell Tower tragedy and the recommendations of Dame Judith Hackett, the CROSS scheme was expanded in 2021 to include fire safety reporting. This year, we were appointed by the Building Safety Regulator to operate the official voluntary occurrence reporting system that is required under the Building Safety Act. So CROSS receives voluntarily submitted reports which are then anonymised and de-identified to ensure that a reader cannot identify any product, location, company or person. The de-identified report is then commented on by our expert panels who use their experience to help professionals understand what can be learned from the report. Following a legal review and a review by the reporter, the report is then published for others to learn from. We have over 700 safety reports that are freely available to view on our website, and we publish a quarterly newsletter that contains our latest reports. The receipt of a number of reports on a common theme could be considered as a precursor to a more significant event, and in these cases, we will issue a CROSS safety alert. For example, over the years, CROSS has received a series of reports regarding balcony safety issues, and this, together with tragic events within the public domain, triggered the release of a CROSS safety alert. This alert highlights the common issues associated with the design, construction, and maintenance of balconies. So many issues that we observe also occur internationally, and CROSS promotes the sharing of lessons learned across our international network. We currently also operate in the United States and Australasia, and the country shown hatched is Germany, and the German Proof Engineering Association are currently in discussions with us, and that we hope that they will come to fruition before too long. So what are we learning from the reports that we receive over the 18 years that CROSS has been operational? I'm sure that many of these will not surprise you. The overarching lesson is that similar issues occur again and again. There is inadequate communication, particularly at interfaces, and divided responsibilities. Tasks are being undertaken by those not suitably competent to perform them. There is ongoing concern about the degradation of older structures, coupled with a lack of maintenance. Changes in architectural or construction trends can have unforeseen consequences. A poor understanding of computer analysis and design is a very common theme of our reports. There is a shortage of suitably qualified and experienced engineers, leading to safety-critical decisions being made by others. There is a lack of competent site supervision and inspection, and this is coupled with inadequate quality assurance and checking. And added to the technical problems are the human traits of carelessness, corruption, and ignorance. However, it is important to say that the vast majority of buildings are indeed designed and constructed safely. So if you've not already done so, we do hope that you'll sign up to CROSS. You can search CROSS Safety or scan this QR code. You'll then get our communications directly. And even if you don't register, you can still search our database for information, and you can submit a safety report. Reports are the oxygen on which we survive, so please do contribute if you can. It may help to make structures safer. Thank you for listening, and we can now move on to the main event. So to introduce our speaker this evening, Gary Klein. Gary is a Senior Principal and Executive Vice President of Wiss Jenny Elsner Associates, and he's based in their Chicago office. For over 40 years, Gary has worked with buildings and other structures that are suffering from deterioration, distress, or failure. And he's investigated numerous structural collapses, including the 1981 collapse of the Skywalks at the Hyatt Regency Hotel in Kansas City, the 1996 collapse of the KB Bridge in the Republic of Palau, and the 2021 collapse of the Champlain Towers South in Florida, the subject of this lecture. For his work in these investigations, Gary was elected to the National Academy of Engineering in 2016. So I'll now hand over to our main speaker, Mr. Gary Klein.
Well, Paul, thank you very much for that very kind introduction, and I was struck by those key lessons, and keep those in mind as I go through this presentation. I think many of those will surface again, right? So we're going to talk about the 2021 collapse of Champlain Towers South in Surfside, Florida. That's a shot of the building before the collapse. By the end of the presentation, you should be able to describe the significant conditions before the collapse, recognize punching shear related distress, which may be very important, right? And parameters affecting flat plate slab performance, summarize the timeline for the pool deck collapse and subsequent building collapse, the progression of that collapse, and explain at least our theory as to the collapse. If you permit me a brief commercial, I'm with Wiss Jenny Elsner Associates. We're headquartered in Northbrook, Illinois, as Paul mentioned, but for about 7 years we've been in London. And WJ is different than most engineering firms. Our entire focus is on problem solving, usually based on instrumentation, testing, research, and detailed investigation. And we're doing that same type of thing here in London. And I should also acknowledge our client. We were hired by the Condominium Association for Champlain Towers South through their attorney, Ackerman, and Michael Goldberg and Brenda Rodmacher did a tremendous job in that they helped coordinate the investigation for the civil litigation, right? Because we had plaintiffs and other defendants all interested in carrying on an investigation, and the association was kind of in the middle of that, and they did a terrific job. The fees were ultimately paid by James River Insurance Company, and their attorneys were involved, Clyde and Company. We want to acknowledge them as well. And also the WJE staff. I'm here representing them. including Matt Fadden, my colleague who really led this investigation. I took the initial call, but he's from South Florida and did a fabulous job, and there were a lot of man hours in field investigation, document review, structural modeling, and geotechnical consulting. And the last thing is a disclaimer. The National Institute of Standards, through their National Construction Safety Team, has elected to investigate this collapse. They're about 2 years into it. Their report's due in another couple of years. And I have served as a advisor to the National Construction Safety Team. They knew about this talk and asked me to be clear that the observations and opinions and findings discussed today are those of WJE and not NIST. Their investigation will be separate, and their report will come out in a couple years. But I have no doubt that they'll do a great job. They have a great team working on that. Today's presentation it follows kind of the steps in the investigation, right? Starting with document review, and that's not just construction document, that's all kinds of, everything that we could get our hands on, including photographs and other things like that during, prior to the collapse. A site investigation, limited laboratory studies, and structural analysis, all leading to a theory of the collapse. All right, so let's start with document review and some background. The building is in Surfside, Florida, and Surfside is north of Miami Beach in that circled area there. A very nice area and becoming more high-end every day. And as of the time of the collapse, on June 24th, we knew that a building collapsed at about 1:30 a.m. 100 people or so were feared missing or dead. The cause was not clear at that time, but there was a lot of speculation, as you might imagine, in social media, and a lot of information, including the permit drawings, which were made publicly available. So the collapsed building you can kind of see is in the middle of that picture. To the left, our left, is 87 Park, and to the right is what's known as the Blue-Green Resort, and I may refer to those buildings later in this presentation. That's what the building looked like after the collapse, and it was really the eastern half of the building that collapsed, and the collapse was arrested due to stairwells and shear walls, roughly that purple rectangle. Just a different view of the collapse. And this one focuses on the pool deck area, and those circled columns indicate where from early on it was apparent their punching shear failures had occurred between the pool deck and the columns, and there'll be a lot more about that. The building was designed in accordance with the South Florida Building Code, the 1979 edition, which in turn references the 1977 edition of the American Concrete Institute Building Code Requirements for Reinforced Concrete, also known as ACI 318. The building was 12 stories, L-shaped in plan, 136 units, and again, built in 1981. It had reinforced concrete flat plate construction, and this is a shot of what we could consider flat plate construction, and that is a flat slab without drop panels or capitals. We define as flat plate. I understand your definitions might be a little bit different. There's parking at the lobby level and the basement garage, and there'll be more slides to explain that, but this shows the basement level garage, which covered the entire site, not just the building footprint. That's important to understand, and I'll show some slides on that. And that's the pool. It looks huge there, and it's a sizable pool, but the pool deck was much, much larger, as you'll see. And the pool deck is where we're going to talk a lot about that. Okay, so there's an overall plan view. Collins Avenue to the west, the Atlantic Ocean to the east, and you can see the perimeter of the building and the pool and the deck surrounding that pool, okay? If I take away the overview, you can more clearly see that the building footprint was smaller than the site footprint. And the next slide that you'll see is one level down, okay? So in one level down, you see that there's parking in the entire perimeter. So the pool deck is a supported slab, all right? Remember that. As part of the review, we looked at the history of what went on in 1996. There was fairly significant activities where they added sand and pavers to the pool deck. There was an engineer who wrote a letter, but this work was primarily driven by a waterproofing consultant. And the pavers look great, but they added weight, and they also concealed to some extent any underlying structural damage. In 2018, they began a recertification effort. In Florida, you have to recertify buildings after 40 years. And that means you have to hire an engineer, they have to do an inspection and do repairs and certify that the building is safe for continued use. So we had the benefit of that partially completed report, or the completed report actually, even though the repairs were not completed. And there was the usual mix of damage, as you might expect in a coastal environment after 40 years. Abundant cracking and spalling in the garage. Previous repairs weren't holding up too well. A lot of concrete repair, and even certain areas around the entrance along Collins Avenue, and even the pool deck slabs showing distress were recommended for removal and replacement. I want to talk about the deck finish. One of the things the recertification engineers was investigate, what do I have on top of this pool deck? Because it wasn't entirely clear from the drawings. Okay, so there you see the pool deck. And here it is in plan view, and the next slide is a closer view of this portion of the pool deck. And I'm showing it to you because they took cores, just 2 cores, but they were very valuable in our investigation is understanding the nature of construction. And one was through a parking area above the main parking area, which was subterranean, but they had a grade level parking area. And that's test core B, and test core A was through the pool deck itself. And the next slide will show those cores. A few observations on these cores. On the left is the core through the parking deck, on the right through the pool deck. What's missing from the pool deck is the sand layer and pavers. They're not part of the core, if you will. But the parking deck showed a topping slab more than 3 inches thick that was not shown on the original drawings. It's not clear if the structural engineer was aware of it. When I say original drawings, we think it's a permit set, so there was a possibility of changes down the line and even design changes. The cores look pretty badly broken up, but in my experience, when you core and you hit a rebar, that often causes a crack, and it's not necessarily true that these cracks were pre-existing cracks, right? They may have already existed. And looking now at the pool deck slab, there was also a topping slab that was below the original tile and mortar, which was part of the original architect specification. So we knew that at least the construction team was aware that they were adding load in the form of a topping slab on top of the structural slab. The overall slab thickness was about right, but the rebar, not so much. There was excessive cover over the top reinforcement, which is not unusual in flat plate construction in our experience for various reasons. But that becomes very important too, and when we get into a discussion of punching shear strength. But what about this extra weight? By extra, I mean that's not shown on the permit set. And in the case of the parking deck, they had some 90 millimeters of topping slab, right, more than 3 inches, that were not shown on the original structural drawings. And they had a 55 millimeter topping slab in the pool deck area, and on top of that, an additional 35 millimeters or so of pavers and waterproofing. Okay, so those items added weight. There was also a sand layer in there, quite a bit of weight to the parking deck and the pool deck. And the planters weren't the same as shown on the original drawings. The planters that were shown on the original drawings and still in place are shown in dark green. As design planters that were not present are shown in kind of a pink color, and added planters are shown in that light green color. So there's several planters were added compared to, again, the permit set of drawings, which added weight in some areas, okay? In looking through the mountains of documents, we came across some calculations that the recertification engineer did. And mostly in these recertifications, they do a visual inspection and fix what they can see is wrong. But at the entrance area along Collins Avenue, they were going to reconfigure the entrance. So they had a different drive pattern, different trucks could enter. So they needed to do some structural analysis. So they undertook kind of a frame analysis along column line T, and that's a north-south column that you can see there, right? And they looked at bending and shear for that area of the entrance, which is supported above the existing garage. And the next slide shows their own output. And so there were 10 supports along that line, and at the far right, it shows the results of the shear stresses at those supports. And of course, the word exceeded appears in every case. So that was a clue, if you will, to the recertification engineer that there might be a punching shear deficiency at the grade level at this structure. As I mentioned, we also had a lot of photographs, videos, and such of the pre-collapse conditions, and they weren't always good. And as you can see on the right, we had to piece things together often to see what the totality of this particular column looked like. But it was of interest to us. It was column L13.1, and I want you to notice the mineral deposits at the base of that column. They're quite extensive, right? And there was evidence then there was a lot of leaks at the slab column junction. And the possibility is when there's more so than just typical cracking, when you have cracking and punching like distress, there's a pathway for water to enter. In other words, in those cases where you have exposure to water, accumulation of a lot of water might be an indication of a punching deficiency, and certainly an indication of cracking around the columns. But that, I'm not sure many engineers would fully appreciate that. But if there was a smoking gun, it was when we discovered this picture. Now, what you're looking at is the pool deck next to some planters, and you're looking south in this particular case, right above column K13.1. And those planters were constructed with what we call concrete masonry units. I think maybe you call them concrete block. Cinder block is another term that I've heard used. And the cracking pattern is consistent with the stress of the underlying slab. You get a horizontal separation, right, along the horizontal joint in those concrete masonry units, which suggests sagging of the slab, right? And there's a lot of deflection in this corner that suggests a problem with the underlying slab. Now, the recertification engineer was aware of this problem, was made aware of this cracking problem, but attributed it to something going on with the planters themselves and not the underlying structure. All right. And what makes it more significant is we have this picture from a year earlier of the exact same location without that distress. So something happened between June 2nd of 2021 and when this distress happened, I mean before June 2nd, 2021, but after April 13th, 2020, that's when this picture was taken. So somewhere between April of 2020 and June of 2021, this distress occurred. And remember that June 2nd, 2021 was only 3 weeks before the actual collapse. And this is a shot of the same area after the collapse, and that green is the planter, right? You can see some of the concrete block units for the planter and a column that had punched through the slab at that location. More about that later. We knew some things from the video that was taken of the parking area. Now remember, this parking area covers the entire site, and not just the building footprint. And to the right is the area below the pool deck, and to the left is the area below some of the units. And you can see the evidence of moisture penetration extensively in that area to the right. And also note that there's a change in elevation. It's very hard to tell, but the electrical and plumbing lines are a clue that there was actually steps in the slab at those locations, right? And that plays in, as we'll discuss. And I want to mention in particular beam A. To help deal with those steps, they needed a beam. So they put in these beam A's that transition from to the building, to the columns along the south side of the main building, if that makes sense. And we had some video. It's amazing how many things are captured in video. And remember I talked about the Blue Green Resort, which was to the north of this building? There were some guests at the Blue Green Resort that heard or felt a whoosh of air come out through what was the entrance ramp to the Champlain Towers parking structure. So they got their video camera and took the shot that's shown at the right. And this is kind of hard to wrap your arms around, but they're looking down the parking ramp underneath the building and into the pool deck beyond, okay? And when you enhance that photograph, you see that the building is standing, but something terrible had happened to the pool deck area beyond. A lot of collapsed debris, possibly failed columns, and so on. And so we had that video evidence. We also had evidence from a ring video at Unit 711, and I'll explain where 711 is. But and so this ring video picked up this motion at around 1:15 to 1:22 a.m. of severe distress in Unit 711, but it's not collapsing at that time. It's just showing a lot of distress. So something went on, and we'll explain that later. So that's where Unit 711 is, right? It's above, it's on the south facade, if you will, at the junction between the pool deck and the building. In Unit 611, the residents reported cracks in the walls, and they escaped, I believe, as did in Unit 111, also got out safely, and they were right at what we believe is the initiation point of the collapse of the tower itself. So we could kind of reconstruct from all of that a bit of a timeline, and that is, and it's sort of color-coded here. So the pool deck, sometime between 1:10 and 1:15 a.m., based on eyewitness reports, 9/11 calls, those kinds of things, it collapses, right? And then there was a gap of some 7 to 12 minutes before the south portion of the eastern tower collapses, beginning at the bottom. And we know that from a video taken from a neighboring property. And 3 seconds later, this area 3, right, the north portion, if you will, of the east tower collapses. And there was a delay of about 8 seconds before area 4 kind of folds in on top of areas 2 and 3. In this area 5, it doesn't collapse. There's a shear wall, if you will, between the east and west portions, so the west tower does not collapse. So keep that timeline in mind. We were eventually allowed access to the site in a frustrating long period of time. Initially, appropriately enough, right? The Broward County, anyway, the county police department took control. It was a crime scene, and they didn't even allow the NIST investigators on originally, and certainly they weren't interested in any consultants coming on behalf of the litigants, right? So we weren't able to get to the site until October or so, and at that point, they demolished the west tower and cleared the site. So this is what we had to work with in terms of a site investigation. But it was still very valuable, and one of the first things we did, and with the help of our client, we organized joint testing protocol, so that we have all these defendant parties and plaintiffs, and they all wanted to do testing, so we agreed on just doing the testing once, and we hired a firm to coordinate all that. And one of the first tests or examinations we did was an elevation survey of the lower level slab, because there's a lot of speculation in South Florida due to the karst formations that it was a foundations problem. And there are contours there, but those contours are in inches, and there's just not a lot of difference in elevation across the building footprint, particularly not very much difference from column to columns, such that subsidence of individual columns was not indicated. There is kind of a low spot in the southeast corner, but there was a sump there for the lower level slab, so it was kind of sloped to drain. So we didn't really see much indication of foundation problems. We did extensive geotechnical investigation and didn't uncover any such evidence. Along with sampling of concrete, right? We took samples of the concrete and the reinforcement, as shown here, and even did things like openings to look at waterproofing and the like. In the meantime, the evidence was collected by the police department in cooperation with NIST and stored in a warehouse out near the airport. And so these are the pieces that they collected. And we were finally allowed access to that, to look at these pieces. And we flew our drone and merged the photograph together to get a collection of all the pieces. So we were able to, and they all had numbers on them, but nobody correlated the numbers with the location in the building. So we all had all this evidence, but we didn't know where specifically it was from. So that was a challenge. And I think they kind of knew, NIST did, but kind of what we heard is, well, rather than give you the wrong information, we'll give you no information. So, but we did learn some things. They also saved some pieces from the imploded portion of Tower 5 in a separate part of the warehouse, which is shown there. This is one of the most important pieces. We could recognize it as a pool deck column based on its various characteristics. There was no column above, and there was an apparent punching failure. You're seeing kind of half. If I can complete that area around the column, it would look something like that with a punching failure right in the middle. And a couple of things I want you to note. Not a lot of reinforcing. What was there was a little bit too deep, just like we saw in those core samples. It was 2.5 inches to what was the bottom layer, and if you kind of superimpose where the top layer should be, it was about 1.25 inches to, I'm using inches again, let's say 30 millimeters or so excess cover, right? And as you will see, that's important to punching shear resistance in Eurocode as well as in the ACI code. And they recovered some columns that were clearly pool deck columns, and some of those even had the parking numbers on them, so we could identify where they were from. That was helpful. And that, I guess I would note that failure pattern, in our view, was consistent with a punch-through failure of that column. We were very interested in beam A. Remember I mentioned beam A, and that's where they used a beam to help facilitate these steps in the slab, and thought that would be a real hint as to how the collapse progressed into the main building. And the beam A's were pretty much destroyed. Now, you can see one example, but all we could do was confirm that the reinforcing was consistent with that shown on the drawings, but we don't know how much damage was due to the collapse itself versus pre-existing damage. And likewise, certain columns into which beam A framed were found, not in the critical area where the collapse initiated, but elsewhere between the building perimeter and the deck area. And a couple of observations are important here. First, as shown on the left, there's a huge chunk that has been pulled out of that face of that column. And we've shown kind of where the rebar should have been, and it was pushed in quite a bit. And one of the things about these columns, they were not all that big, and they were very heavily reinforced. Nominally almost 7% reinforcement. But then when you splice 7% with 7%, you get 14% reinforcement. That's a lot of reinforcement in a column, and they didn't use offsets to splice them carefully, so they ended up with this excess cover, which made these columns vulnerable to those kinds of breakout failures. And you can identify where those purple arrows are, where the beam A reinforcement came into the column. So we knew where we were in these 16 by 16 columns. Okay, now moving on to laboratory testing. This is from the Joint Testing Protocol. I'll just kind of go into the findings. The concrete was typical to Florida. Moderate water cement ratio, well mixed, not air entrained, which was not unusual for South Florida. The corrosion of the reinforcement was consistent with that at placement. In other words, you put these bars out in South Florida and they rust, right? And you put concrete around them and they stay rusted. But we didn't see much corrosion beyond that, right? Even back to that slab sample I showed you, you didn't see characteristic delaminations that you might get at a top mat, for example, right? And the chloride levels, and these are mostly samples from the basement slab, not from the pool deck slab, but they were very low. And you see the carbonation front in the photograph to the left, and it wasn't terribly deep. So nothing from materials standpoint stood out. And we did have a chance to test cores, some from the pool deck, and I'll mention those in particular, where the average compressive strength was 30 newtons per millimeter squared, which exceeded that specified, not by a large margin, right? So it wasn't, and concrete can gain strength over time, but it certainly didn't indicate that concrete strength was a major factor. There were a couple of columns where the measured strength was lower, but we don't think that played a role. Oops. And likewise for the reinforcement, the yield strength and ultimate strength and elongation, which is how we evaluate reinforcement in the U.S. and I suspect here as well, all of them met those standards and came in, higher by about the amounts expected for reinforcement. And finally, structural analysis, and we want to dive into our friend punching shear. I've been talking a lot about that, right? And I showed you this slide already of all of these columns poking up through the pool deck. And when you say punching shear, we're talking about the kind of failure shown at the right. And that was the stress also indicated by this photograph, right? The smoking gun, as I called it. Well, in U.S. practice, punching shear is evaluated using the equation. I apologize for showing a complicated equation, but V sub C is 4 times the square root of F prime sub C times a perimeter B naught and an effective depth D, okay? So it's a function of B naught and the effective depth D with the coefficient of 4, and I've showed the metric equivalence, but it's an unusual equation in that the units don't work out right. I mean, you have a square root of a pounds per square inch. It doesn't make any sense, but as long as you keep track of your units, it works out. And again, in Eurocode practice, and I think the UK, you have different formulas for both on the resistance side and even the location of the perimeter and so on. But and the results aren't wildly different, but your design equations are different. But one of the things we noted that recent research, by recent last couple of decades, has shown that that coefficient of 4 is dependent on flexural reinforcement. In other words, and this shouldn't be a surprise to the structural engineers, there's a relationship between bending strength and flexural strength. And Mutani did a lot of work on that, and he talked about flexurally driven punching failures, where the coefficient could be much less than 4 when there isn't very much reinforcement. And this was a case in point. They had very little, very light top reinforcement. In fact, they had deficiencies in flexural strength, okay? We built a finite element model to verify the forces acting at all of the elements of structure and use it for various purposes in the investigation. So we want to focus in on this column K13.1 where I showed you that they had the distress earlier, right? And this is kind of a simplistic structural review in this particular case based mainly on tributary area, but the resulting shear transfer was very consistent with that finite element model I showed you, right? And in any investigation, it's important to look at the quality of design and the adequacy of the design, but also the conditions at the time of the collapse. One is to evaluate, was there a design mistake? The second is to better understand, does the collapse make sense, right? So focusing on the as design number for this column K13.1, you see the column size there is 400 by 300 millimeters, the specified strength, the clear cover, and what we call factored load, right? When you design for punching shear, you factor the dead load by 1.2 and the live load by 1.6. And so you get this factored load. And you take the strength from the 4 roots of F prime sub C and you multiply that by a strength reduction factor. And that's a partial safety factor similar to the materials factor that you use, but it's meant to take in to account other effects. So what you find when you do that evaluation is that the demand, the factored load, exceeded capacity by 72%. So it was way under-designed at that particular columns, and others were similarly under-designed. Now at collapse, we have a very different condition. We don't have any live load, right? The actual strength was a little higher. The clear cover was lower, so the effective depth was lower. And so when we get done with all that, we have the demand is not quite as much as capacity. It's only 0.85, but that's using a coefficient of 4. And remember I talked about light reinforcement and that maybe a coefficient of 3 is more like it. So if you use a coefficient of 3, you find that demand exceeds capacity by about 13%. So I think between the light reinforcement and the extent these design codes can predict the strength, that explains the collapse, right? The collapse in the absence of live load. And we find also, and this just shows it one model from a computer output, the flexural strength was also deficient. So there's an interaction between shear and flexure. We've known that for one-way shear and beams for a long time. For two-way slabs, we're maybe just beginning to understand that. So all that leads to a theory of collapse. And I have some slides here that kind of illustrate this theory, but I want you to try to follow along. The pool deck to the south of the building fails. We know that from the video site observations, that this whole thing started with a punching shear failure. And as it fails, it applies horizontal forces to the building columns, and I'll show you an illustration of that. The forces are due to both bending and catenary behavior. And the detail due to the step in the slab is somewhat diminishes the strength and makes it vulnerable to progressive failure. So these forces that fail the column at the south exterior wall of the building, resulting in progressive and partial collapse of the tower, specifically the east tower. And the remaining western portion remains because the collapse was arrested by the shear wall. So let me illustrate that theory. Here we are again looking at the pool deck along column line K. All right, and I think the next slide you'll see, it's kind of a 3D view of the framing at that location. I've showed you this before where beam A frames into the building is to the right in blue, and the pool deck to the left in a pinkish color, and beam A is shown there, and that was the framing detail. And I want to illustrate this in a different way. This is a cross-section view looking west through the pool deck and a portion of the building, including the portion column line 9.1, where beam A frames into the building. And remember the planters? And I showed you that before April 13th, 2020, there really wasn't much indication of distress in the planters. shear and flexural cracks were highly likely, we think, in the slab column junction regions, but it hadn't manifested until sometime. So that's the photograph before April 13th, 2020. But then sometimes after April 13th, 2020, but before June 2nd, when this photograph was taken, something happens at that particular column that causes the slab to sag, and you get those horizontal cracks and the faulting, if you will, at the reentrant corner, which is consistent with sagging of the slab and concentrated rotation at column K 13.1. Okay. So that's bad. And hung on there for at least 3 weeks or so. And then a punching shear failure developed. We're not certain it started at K 13.1. It's the most likely candidate because it was the most heavily loaded and it had that indications of damage from the photographs before the collapse. So that's a likely suspect. So when that happens, then what happens? The adjacent columns, right, they're going to pick up a lot more load, and they will fail almost instantly in punching. So you get this condition here where several columns fail in punching, and now notice what happens to beam A. Beam A drops, and it has both catenary forces, if you will, kind of pulling, as well as bending forces where the top portion of the beam is pulling on the columns along line 9.1. That makes sense, okay? And then the pool deck collapses. And as we've seen in the videos, there was indications that the building in that immediate area around K 9.1 also sagged somewhat, okay? Dropped a little bit. So the next few slides concentrate on that area. And this is the detail of the beam A connection, if you will, to the south building columns. And imagine a shear force and a pulling force on beam A. Well, that's going to pry out that chunk of concrete. We showed you a picture of that, and the vulnerability to that kind of breakout failure was exacerbated by the fact that, at least in the case of the one column we saw, the reinforcement was moved over to accommodate the splice. All right. So when that happens, the building drops, and we think it dropped several inches and held. It held for, what did we say, 7 to 12 minutes or so before the building collapsed. But you know, concrete strength is time dependent, and after those 7 to 12 minutes, then the columns give up the ghost, and the east portion of the building collapses. So, what mistakes were made? And first and foremost, the pool deck slab was inadequately designed by a factor of almost 2. And there was excess weight. Remember, they added pavers, they added sand, there was an overlay that may or may not have been accounted for in the original design. We know the design was very deficient by some 72%. The top reinforcement was too shallow, right? And so you lost effective depth. So those first 3, if you will, were the main deficiencies that contributed to the collapse as regards the original construction. But we couldn't help but list that the engineers responsible for the recertification failed to recognize some of the warning signs, right? The smoking gun, as I called it, right? So those mistakes appear to have contributed. But were there other factors? We think so. And first and foremost, it's sustained load effects. You take a concrete cylinder and it breaks at 4,000 PSI. I'm sorry for the English units again. They are, after all, English units. We got them from you. We just never. But load that same cylinder at 3,000 PSI, it may eventually break due to micro cracking and creep, right? And so concrete is weaker under sustained load, and this particular structure had sustained loads near the limit for some 40 years. the low top reinforcement ratio. Now, I don't mean the reinforcement itself was shallow. Now we're talking about the ratio reinforcement. There weren't very many bars concentrated around those columns, and that there should have been. And that's been corrected in current codes, at least in the U.S., that you have to have a greater concentration of reinforcement in that vicinity to kind of address that flexually driven punching failure, if you will. Water buildup in planters may have been a factor. We couldn't rule out corrosion. We didn't see evidence that it was significant in the few samples that we were able to examine, but we didn't examine everything, right? So that's also a potential contributing cause. The county appointed Judge Hanneman to serve as the judge in the civil litigation, and he did a phenomenal job, and was able to bring sides together and try to get, if nothing else, at least swift justice for the plaintiffs. Some 98 people lost their lives, and in the end, the case settled for $1 billion from various defendants plus defendants, plus another 120 million from sale of the property. A huge verdict, whether it's justice is a different story. But, you know, the original designer and builder weren't around, but they found other defendants that contributed. But from a legal perspective, very successful in that it got wrapped up quite quickly with a pretty satisfactory judgment, at least from the plaintiff's point of view. So what should we do going forward, right? It goes to what Paul is trying to do with Cross, and we just have a few thoughts about that. And in our current practice, there have been changes to the ACI code that address some of the problems, particularly the concentration of reinforcement. And I think this case emphasizes the importance of what we call peer review for important buildings, that a second engineer take a look. Just to submit these to a building department, this just can overwhelm a local building department in terms of doing an adequate structural review. So many will require a review by another a licensed structural engineer in the jurisdiction. And that came out of that Kansas City case, that's a good idea, but it's not mandated, but it's practice, it's encouraged and followed. Certainly this case raises questions about how often buildings are recertified and what that process looks like. How much do you delve into the original design, particularly in flat plate construction. And maybe other changes related to punching shear. The fact that the reinforcement was low was not unusual in our experience. It happens fairly frequently, and maybe there needs to be tougher standards around that. I mean, think about it. These top reinforcing is supported on chairs. The construction workers are walking all over it and then pouring concrete on top of it, and you really can't see if it is sunk further. Or maybe they use the wrong chairs. We don't know. And there's probably some future research needs as well to better understand punching shear resistance and progressive collapse. Paul and I had a conversation around that, and that's a tough thing to codify, but it is unfortunate, maybe unconscionable, that the collapse of a pool deck, which would have at 1 in the morning would have gone without injury to anyone, and they could have recovered from, to a building collapse, right? It progressed, and anticipating that is hard, but I think that this case is going to focus more attention onto progressive collapse and other research related to punching shear. And that's all I have.
Thank you, Gary, for that very interesting and informative presentation. If we look at the Swiss cheese model of failure, it appears that we had some perfectly aligned holes in the collapse of Champlain Towers South. Firstly, we had inadequate initial design of the poolside slab. This was coupled with poor construction and misplaced reinforcement, leading to a reduced effective depth. followed by an unconsidered increase in the dead load on the slab with the introduction of new paving, fill and the addition of more planters. So these and other contributing factors led to a low margin of safety and the eventual failure through progressive collapse of the main tower. So, incredibly interesting lecture.